So let's look into linear algebra today. There are basically two major issues. One is the matrix eigenvalue problem, and the second one is solution of linear systems. So let's begin with the matrix eigenvalue problem. All of us know that if A is a square matrix, the equation Ax is equal to lambda x defines a system of homogeneous equations. The lambdas are called the eigenvalues or spectral values of A, and the x's are the corresponding eigenvectors of A. Now, in order to determine the lambdas and x's, determinant A minus lambda I is equal to 0 is a necessary condition. This equation produces a polynomial equation in lambda of the order of A. That is, if A is 4 by 4, we will get a biquadratic equation in lambda. Then you solve this equation and you get the eigenvalues of A, and then corresponding to each eigenvalue we can compute the eigenvectors. So to compute eigenvectors, we solve the homogeneous system A minus lambda I into x is equal to 0 such that the vector x is a non-zero vector. So the definition itself requires that the vector x should be non-zero. So eigenvectors must be non-zero vectors. So let us see how we can solve the matrix eigenvalue problem with the best methods available before us. Now let's look at some basic issues before launching into problems. The first thing is, sum of the eigenvalues is equal to the trace of the matrix. Product of the eigenvalues is equal to the determinant of the matrix, and for a 3 by 3 matrix A, the characteristic equation can be directly constructed by the rule lambda cube minus A lambda squared plus B lambda minus C is equal to 0, where A is the trace of A is the trace of A, C is the determinant of A, and B is the sum of all 2 by 2 principal, minor determinants of A. By using this rule, we can avoid the elaborate expansion of determinant A minus lambda I is equal to 0, which will take away most of the time. So once a characteristic equation can be built quickly, solving that for eigenvalues and then subsequently eigenvectors becomes much easier. So let's look at some of the fundamental problems that are expected, which we can solve in a couple of minutes. So let's begin the exercise. Okay, let's take the first question. If A is a matrix 8 minus 4 2 2, what will be the trace of A cube? Now all of us know trace of A cube is the sum of the diagonal elements of A cube. But a student who knows the eigenvalue problem will never find the A cube matrix and then take the trace. Instead, he will find the eigenvalues of A and then use a special property by which the trace of A cube can be predicted. So let's find the eigenvalues of A. So let's write the characteristic equation, which will give us lambda square minus 10 lambda plus 24 is equal to 0, giving lambda is equal to 6 or 4. So these are the eigenvalues. Now trace of A, even though it's not required, will be 10. So what we require is trace of A cube. This is nothing but 6 cube plus 4 cube, which is 216 plus 64, which is 280. So the trace of A cube will be nothing but the sum of the eigenvalues of A cube, which is lambda 1 cube plus lambda 2 cube. So that's how you get 280, and the correct option for this problem is A. So one can use properties of eigenvalues to do long calculations. Otherwise, you will get lost into making long calculations which are unnecessary. Let's go to the next question. Question number 2. What is the algebraic multiplicity of the matrix 2 1 1 1 2 1 0 0 1? The concept here is we will first find the eigenvalues of the matrix. Of course, you must produce the characteristic equation as quickly as possible. Now once the eigenvalues are there, the number of times an eigenvalue is repeated is called its algebraic multiplicity. Now basically what we want here is the algebraic multiplicity of the smallest eigenvalue. So let us find the characteristic equation of this matrix first. Lambda cube minus A lambda square plus B lambda minus C is equal to 0. As explained, A is equal to the trace of A, this is 5, B is equal to the sum of all principal minor determinants which is 4 minus 1 3 plus 2 plus 2, so this is 7, and C will be the determinant of A. So let's expand by the third column. You will get 1 into 4 minus 1, which is 3. So we can write the characteristic equation as lambda cube minus 5 lambda squared plus 7 lambda minus 3 is equal to 0. So you can easily see that the sum of the coefficients in this case is 0. Therefore, lambda is equal to 1 will be a confirmed eigenvalue, and from this quadratic equation lambda square minus 4 lambda plus 3 is equal to 0, use lambda minus 1 into lambda minus 3 is equal to 0. So the spectrum is the collection of all eigenvalues 1 1 3, and the smallest eigenvalue is 1, which is repeated twice. Therefore, the algebraic multiplicity of 1 is 2, because this is repeated twice. If the question was what is algebraic multiplicity of the largest eigenvalue, because 3 occurs only once, then the algebraic multiplicity would be 1 for 3. But for the smallest eigenvalue, it is 2. And the correct option for this problem is C. Let's go to the next question. Question number 3. What is the characteristic equation of the matrix 1, 1, 3, 1, 5, 1, 3, 1, 1? So going by the fast track method, A will be trace of A, which is 7. B will be the sum of the determinants 1, 1, 1, 5, 5, 1, 1, 1 plus 1, 3, 3, 1. So this would be 5 minus 1, 4 plus 5 minus 1, 4 minus 8, which is 0. And C is determinant of A, which is 1 into 4 minus 1 into minus 2 plus 3 into minus 14. So this will be 4 plus 2, 6 minus 42, which is minus 36. Accordingly, the characteristic equation should be lambda cube minus 7 lambda squared, no linear term because B is 0, minus of minus plus 36 is equal to 0. Therefore, the correct option for this problem is C. Let's go to the next question. Let's go to the next question. Question number 4. If D is the matrix of eigenvalues of a matrix and P is the corresponding modal matrix, then what is the formula to retrieve A? Now this problem is based on the concept of similar matrices. We say B is similar to A if there exists some non-singular matrix S such that B is equal to S inverse AS. This is a formal definition of similar matrices, and an extension of this particular concept is every square matrix A is similar to the matrix D of, where D is a diagonal matrix, the matrix D of eigenvalues of A. Accordingly, from this definition we can write D is equal to P inverse AP. Now the very important thing is, instead of the non-singular matrix, we must replace it by the matrix P, where P is the modal matrix. P is the modal matrix. From this, by pre-multiplication by P and post-multiplication by P inverse, we will get P D P inverse is equal to P P inverse AP P inverse. So this is I, therefore we get the formula A is equal to P into D into P inverse. So this is the formula by which the matrix A can be retrieved, provided you know the modal matrix and the matrix of eigenvalues. D should be the diagonal matrix of eigenvalues of A. So the correct option for this problem is B. This is a conceptual question, therefore can be remembered directly. Question number 5. We have a matrix B whose order is 3 by 3. It has eigenvalues 2, 2 and 8. Then what is the trace of B plus determinant of B? This is a direct question because if the lambdas are two, 2 and 8, then trace of B is 2 plus 2 plus 8, which is 12. Determinant of B is the product of eigenvalues, which is 32. Therefore, trace of B plus determinant of B will be 12 plus 32, which is 44. Therefore, this is a simple direct application of the principles of eigenvalues, and the correct option for this problem is B. Let's go to the next question. Question number 6. If A is a matrix 1, 2, 2 minus 1, then what is the output of A to the power of 8? One, 2, 2 minus 1. What we require is A power 8. Of course, no student who has seen a good course on linear algebra will be so naive to calculate A power 8 directly. So, if we know the eigenvalue properties, then this is very simple to compute. Now, there are two approaches to this problem. One approach is through the so-called Cayley-Hamilton theorem, and one is through the process of diagonalization. The diagonalization process is pretty cumbersome for this problem. So, let us look at the Cayley-Hamilton theorem's application. First, let's get the characteristic equation by the formula determinant A minus lambda is equal to 0. Lambda minus 1 into lambda plus 1 minus 4 is equal to 0. This will give us lambda square minus 5 is equal to 0. Now, the Cayley-Hamilton theorem says that every matrix will satisfy its characteristic equation. Accordingly, we can write this as A square is equal to 5i. A power 8 can be directly written as A square to the power of 4, which is 5i to the power of 4. This is 625i. So, you can see how fast one can calculate A to the power of 8 if you know the characteristic equation. So, you can see from the options that D is the correct answer. The process of diagonalization can also produce a result, but that requires finding out the eigenvectors, construction of the model matrix, and so on and so forth. That is not worth for this particular problem. Next question, please. Question number 7. If A is a square matrix with model matrix P, then what is the output of P inverse AP? I think this has been already answered in the context of similar matrices. A will be similar to the matrix D. This is the diagonal matrix of eigenvalues of A. So, every square matrix will be similar to the diagonal matrix of the eigenvalues of A. Therefore, we can write D is equal to P inverse AP, where P is the model matrix of P, matrix of A. In fact, we can also remember that D can be written as P cap transpose A P cap as an alternative formula for D, provided P cap is an orthogonal matrix whose column vectors are normalized eigenvectors of A. And when I say an orthogonal matrix, it also means that these normalized eigenvectors will be mutually perpendicular. So, that is a very important relation in the whole of matrix eigenvalue problems. So, you can choose this or this. In this particular case, we have this option which is declared in the set of options, and you will find that is the option C. So I would recommend students remember both these things. This is when the orthonormal vectors are constructed, and this is when plain eigenvectors are constructed. So let's go to the next question. Question number 8. What is the modal matrix that diagonalizes the matrix A is equal to 5, 3, 3, 5? So we have to compute P in such a way that the construction of this P will lead to diagonalization of A. So what does P contain? P contains eigenvectors of A. But eigenvectors don't by themselves come. You have to first get the eigenvalues. So let's get the characteristic equation of A as determinant lambda minus 5, 3, 3, lambda minus 5 is equal to 0. Lambda minus 5 whole square is equal to 9. So lambda minus 5 is plus or minus 3. So lambda is equal to 8 or 2. You can cross check. The sum of these eigenvalues will be exactly equal to the trace. 5 plus 5 is equal to 8 plus 2. Now, we have to get the eigenvectors corresponding to 8 and 2. Eigenvectors. So let's take A minus lambda I into x is equal to 0. Case 1, when lambda is 8. Put lambda is equal to 8 here. You will get minus 3, 3 and 3, 3 into x is equal to 0. These two are linearly dependent rows. Therefore, let's take the first row. 3x1 plus 3x2 is equal to 0. That is x1 plus x2 is equal to 0. x1 is equal to minus x2. So we can get the vector as 1 minus 1 transpose or minus 1 1 transpose. We can use any of these two as the eigenvectors corresponding to lambda is equal to 8. Then in the second case, when lambda is equal to 2, again from here we will get minus 3, 3, 3, minus 3, x is equal to 0. Again these two are linearly dependent. Therefore, we can write minus 3x1 plus 3x2 is equal to 0. Minus x1 plus x2 is equal to 0. x1 is equal to x2. That means 1 1 transpose is the corresponding eigenvector. So now you can build the matrix P by putting these two vectors in columns. If you choose this and this, you will get 1 minus 1 1 1. If you choose this and this, it will be minus 1 1 1 1. So both of them are accepted, but in the given list we will find that B is the correct option. So it is this matrix which will diagonalize the matrix A by the rule D is equal to P inverse AP. Of course, we are not interested in this. It is only to explain what can be done after the model matrix is constructed. So B is the correct option for this problem. Let's go to the next question. Question number 9. The eigenvalues of the matrix A is equal to 4, 1 plus I, 1 minus I, 10 are of what nature? Now, if you carefully look at this matrix, A is equal to 4, 1 plus I, 1 minus I, 10. The diagonal elements are real. These are real. And the cross diagonal elements are conjugate complex numbers. Any such matrix whose principal diagonal elements are real and the cross diagonal elements are complex conjugates will be called a Hermitian matrix. And one property says eigenvalues of a Hermitian matrix are always real. And to refresh your memory, a Hermitian matrix will have the property A is equal to A conjugate transpose, which is also written as A is equal to A star. That is only for general information, but the eigenvalues of any Hermitian matrix will always be real. Another matrix which will have only real eigenvalues will be a real symmetric matrix. The correct option for this problem is C. Next question, please. Question number 10. What is the nature of the eigenvalues of the matrix A is equal to I by 2, root 3 by 2, root 3 by 2, I by 2? This is a complex matrix in which we can observe a very interesting pattern. First, let us calculate A conjugate. This is minus I by 2, root 3 by 2, root 3 by 2, minus I by 2. From this, we can calculate A star, which is the transpose of this matrix. This will be minus I by 2, root 3 by 2, root 3 by 2, minus I by 2. And if you take the product of A and A star, this will be I by 2, root 3 by 2, root 3 by 2, I by 2 multiplied with minus I by 2, root 3 by 2, root 3 by 2, minus I by 2. Using the fact that I square is equal to minus 1, if you do matrix multiplication, this will be minus I square by 4, which is 1 by 4, plus 3 by 4, so that is 1. And root 3 I by 4 minus root 3 I by 4 becomes 0. Symmetrically, this becomes 0. And finally, second row into second column will give us 1. So you get an identity matrix. So because A into A star is equal to I, the matrix A is a unitary matrix. And one very important property says that the eigenvalues of a unitary matrix are of unit modulus. The meaning of this is the eigenvalues may be real or complex, but the modulus of those eigenvalues will always be equal to 1. That means all the eigenvalues of a unitary matrix will lie on a unit circle. And the correct option for this problem is B. So one has to go through all the properties of eigenvalues in order to avoid very long calculations. You can also see there's an option D which says cannot predict. That is wrong, because you can always predict the nature if you know what type of matrix is being given to you. So let's go to the next question. Question number 11. What is the eigenvector corresponding to the largest eigenvalue of the matrix 1, 6, 1, 1, 2, 0, 0, 0, 3? Now let us discuss this problem. We want the eigenvector corresponding to the largest eigenvalue. But unless you solve for the eigenvalues, you will not know which is the largest. So characteristic equation. Lambda cube minus a lambda square plus b lambda minus c is 0. A is equal to 6, b is equal to determinant 1, 6, 1, 2 plus 2, 0, 0, 3 plus 1, 1, 0, 3. which is 2 minus 6, minus 4 plus 6 plus 3. This is 9 minus 4, 5. And C is equal to determinant of A, which is 3 into 2 minus 6. So it is minus 12. So lambda cube minus 6 lambda square plus 5 lambda plus 12 is equal to 0. So let's try to find out the eigenvalues. 1, minus 6, 5, 12. Now you must see for any standard patterns, sum of the eigenvalues is not equal to 0. So therefore lambda is equal to 1 cannot be an eigenvalue. But you can see that the sum of the odd coefficients is equal to sum of even coefficients. That makes lambda is equal to minus 1 a guaranteed eigenvalue. So if you factorize this quadratic, you will get lambda is equal to 3 or 4. So minus 1, 3, 4. These are the eigenvalues, and we are looking for the eigenvector corresponding to the largest eigenvalue. So we are interested in the eigenvector of lambda is equal to 4. So you take a minus lambda I into x is equal to 0 with lambda is equal to 4. So from this matrix I will get 1 minus 4 is minus 3, 6, 1, 1, 2 minus 4 is minus 2, 0, 0, 0, 3 minus 4 is minus 1. So now I should solve this system of homogeneous equations for x. We can do by a fast method. We will take two non-parallel rows here, that is linearly independent rows, and solve them. Suppose we take these two. So applying the method of cross multiplication, we will get 6, 1, minus 3, 6, that is B, C, A, B. Now we are taking second and third rows, so therefore let's change it. Minus 2, 0, 1, minus 2, that is B, C, A, B, and 0, minus 1, 0, 0. So from this, x1 by 2 is equal to x2 by 1 is equal to x3 by 0. These are nothing but the determinants of this 2 by 2 matrices. So what is that we observe? We observe that the vector is 2, 1, 0 transpose. So this is the eigenvector corresponding to the largest eigenvalue of A, and the correct option for this problem is B. Question number 12. What is the nature of eigenvectors corresponding to distinct eigenvalues of real symmetric matrix? Now this is a very important basic principle of the eigenvalue problem. What it says is, if A is a real symmetric matrix with eigenvalues distinct, that is lambda 1 not equal to lambda 2 not equal to lambda 3 and so on, then corresponding eigenvectors say x1, x2, x3 and so on will be mutually orthogonal. So we have just discussed this very important property about real symmetric matrices. Of course, what happens to the vectors when the eigenvalues are not distinct? Then it's a slightly longish process. by what is known as the orthonormalization process, even vectors which are not orthogonal can be made orthogonal. There is a separate procedure for that, but right now, if the eigenvalues of a real symmetric matrix are distinct, their vectors will definitely be mutually perpendicular. This is a very fundamental principle that all students may remember. So let's see under the options, we have got option B as the correct one. So let's go to the next question. Question number 13. B is said to be similar to a matrix A if there exists a non-singular matrix S such that. That means we are asking for the mathematical definition of similar matrices. This has already been discussed. What we discussed earlier was B is similar to A if there exists a non-singular matrix generally S such that B is equal to S inverse AS. Now, this can also be slightly modified. If you pre-multiply by S and post-multiply by S inverse, or you will get A is equal to SB S inverse. So the options can be given either like this or like this. Both are equivalent. Also, from here, if you only pre-multiply with S, SB is equal to S inverse AS will give us SB is equal to, this is I, so you get AS, or AS is equal to SB. So the similarity of two matrices A and B in the present context can have any one of these three options. All of them are equivalent. As far as this problem is concerned, this option can be seen as option C. This is the correct answer as far as this is concerned. But one may remember all the three things as being similar to each other. Next question, please. Question number 14. If A and B are similar matrices and X is the eigenvector corresponding to the eigenvalue of A, then the eigenvector of B given P is the modal matrix of A with orthonormal columns will be what? Now this is a very important question. Suppose A and B are similar. That means B can be written as S inverse AS. There are two very interesting properties to be remembered about similar matrices. One is eigenvalues are the same, because if you carefully work out, both of them will have the same characteristic equation using this definition. Number two, the eigenvectors are not the same. Eigenvectors are not the same. Then how shall we remember? If X is the eigenvalue of A and not eigenvalue, eigenvector of A, then the corresponding eigenvector of B will be, there are two options. One is P inverse X. The second thing is P cap transpose X. Both are correct. But in this question, it has been given that the modal matrix consists of orthonormal vectors. Therefore, this would be perfectly alright. In fact, this is also true, this is also true. Both the options are correct, but this would be the better one. So because both the options are available, we can tick off both of them. But suppose this was missing, then this would be the correct option. As far as this question is concerned, options B and C are both possible answers. Let's go to the next question. Question number 15. If A is a square matrix with model matrix P, what is the formula to compute e power A? So, A can be written as PDP inverse using the concept of similarity matrices. P is a model matrix of A and D is the diagonal matrix of eigenvalues of A. Now, if you look at e power A, you can use the definition I plus A square by 2 factorial and so on. And I can be written as PIP inverse because this will lead to I only. A can be replaced by this PDP inverse. A square from here will be PD square P inverse by 2 factorial and so on. If you take P common on the left and P inverse common on the right, you will get I plus D square by 2 factorial and so on. But one can easily recognize this is the expansion of e power D. So, e power A can be computed by the formula P into e power D into P inverse. So, the correct option for this problem is B. Question number 16. Given A is equal to 1, 4, 2, 3, what is the output of the matrix B is equal to A power 5 minus 4A power 4 minus 7A cube plus 11A squared minus A minus 10I? Well, we'll go through the Cayley-Hamilton theorem and first calculate the characteristic equation. Determinant 1 minus lambda, 4, 2, 3 minus lambda is equal to 0. So, lambda square minus 4 lambda plus 3 minus 8 is minus 5 is equal to 0. Using the Cayley-Hamilton theorem, A square minus 4A minus 5I is equal to 0. So, we can use this to simplify that particular equation. Suppose you take this block. So, B can be written as A cube into A square minus 4A and the rest as it is. A square minus 4A from here is 5I. So, this can be replaced with 5I. If you replace it with 5I, you get 5A cube minus 7A squared, 7A cube again, plus 11A squared minus A minus 10I. So, reduce this and you will get minus 2A cube plus 11A squared minus A minus 10I and so on. So, you keep on recycling this equation. Keep on recycling this equation into that and you will find that finally C for this particular expression can be found. Of course, you have to be very careful to see that you make the proper substitutions. A square minus 4A is equal to 5I. Okay. So, therefore, again what we will have to do is look into this one. Maybe you can take in fact, you can use this equation as A square is equal to 4A plus 5I, from which A cube can be calculated as A into A squared, where A square is this one. So, you keep on doing like this and you will find option C is the correct option for this problem. You can reduce it to the A and I level. The matrix is of 2 by 2 order. Therefore, generally we have to reduce it to below A square level. that is below the degree of the characteristic equation. So because this is quadratic, we have to reduce it to lesser than that degree. So you will find that is the answer. Next question. Question number 17. What is a condition that the system of equations Ax is equal to 0 has non-trivial solutions? Now this is a fundamental question, and we all know this is called a homogeneous system of equations. Now any homogeneous system of equations can produce only trivial solutions in one case, or it can have non-trivial solutions in another case. Of course, trivial solution is always a solution. Now the conditions for only trivial solutions is determinant A not equal to 0 when A is a square matrix, or rank of A is equal to n. Both are equivalent. In this case, determinant A should be equal to 0 or rank of A should be less than n. Now in this question, we are supposed to give the conditions for the existence of non-trivial solutions. Both of them are correct. Both are seen in the options. So you can see C as well as D are the options for this problem. It's a fundamental question on which numerical problems can be set. Next problem. Question number 18. What are the values of B for which the system of equations 2x plus 3by plus 3b plus 4 into z is equal to 0, x plus b plus 4 into y plus 4b plus 2 into z is equal to 0, and x plus 2 into b plus 1 into y plus 3b plus 4 into z is equal to 0 has non-trivial solutions. We all know when you have a homogeneous system of equations with A as a square matrix, this is the condition for existence of non-trivial solutions. So given that the system has non-trivial solutions, what is the choice for B? So just take the determinant of this and equate it to 0. So this is a thing that anybody can do, but however, let me expand by the first column, 2 into b plus 4 into 3b plus 4 minus 4b plus 2 into 2 into b plus 1 minus 1 into 3b into 3b plus 4 minus 2 into b plus 1 into 3b plus 4 plus 1 into 3b into 4b plus 2 minus b plus 4 into 3b plus 4 is equal to 0. You can see that you are going to get a quadratic equation in B. So that will give us two values of B. And if you solve that equation, you will find B is equal to 0 or 3 as the answers. So looking into the option C is correct. So the only tedious thing is to carefully expand this determinant, build the quadratic equation, and you can clearly see the constant term will be 0. Therefore, B is equal to 0 is one of the answers and the other one is 3. Next question please. Question number 19. What is a vector orthogonal to both the vectors 1, 2, 2 and 2, 1, minus 2? Now you can see that these are two vectors and we want a third vector. Let us call this ABC transpose such that it is orthogonal to both these things. Suppose you call this vector as x1, that vector as x2 and this required vector as x3. The condition is x1 dot x3 should be 0 and x2 dot x3 is equal to 0. So under these two conditions, this vector must be designed. Accordingly, if you take the dot product, you will get a plus 2b plus 2c is equal to 0 and 2a plus b minus 2c is equal to 0. So let's solve this by the method of cross multiplication. And you can rescale it. 2 minus 2 1 transpose. So this is the vector which is orthogonal to both these things. So simple vector algebra principle, and you can see the correct option for this problem is B. Next question please. Question number 20. If Ax is equal to B is an overdetermined system of linear equations, then the system has what type of solution? This is a question. When you are given a system of equations Ax is equal to B, this is called overdetermined if m is greater than n, where m by n is the order of A. So that means it will have more number of equations than the number of unknowns to be determined. All such systems do not guarantee a solution. They do not guarantee a solution. Sometimes a solution may exist, and in which two cases are there. You may have a unique solution or you may have infinite solutions. The third one is a distinct possibility where the solutions may not exist. So whenever a solution cannot exist because of the inconsistency problem, we can still produce an approximate solution to this system. So it is possible to determine an approximate solution if no solution exists by two methods, which is slightly difficult to discuss. One is by using pseudo inverse of A, and one by using QR factorization of A. So wherever no solution exists, you can force an approximate solution to the system by any one of these two methods. So you can find that option C is available, which can be used. Let's go to the next question. What can be said about the set of vectors 1 1 transpose, 1 0 minus 1 transpose and 2 minus 1 0 transpose? The available options are they are linearly dependent, linearly independent, can be transformed into an orthonormal set, or cannot be transformed into an orthonormal set. Luckily in this problem, the number of vectors is equal to the dimension of each vector. So if you can actually take the determinant, we will be able to get some insight into the nature. So this will be minus 1 into 1 plus 2 into minus 1. So this will be minus 1 minus 1 minus 2 is equal to minus 4, not equal to 0. Therefore, this is a linearly independent set of vectors. And you can find that option B is available. Therefore, this can be given. Let us also look for other things. You can see that when you take the dot product of these two, suppose you call this vector as x1, you call this vector as x2, and this vector as x3. x1 dot x2 will be 1 plus 0 minus 1 0. x1 dot x3 will be 2 minus 1 plus 0 not equal to 0. So therefore, it is not an orthogonal set. In an orthogonal set of vectors, all the three must be mutually orthogonal, that is perpendicular. But whenever we have even non-orthogonal vectors which are linearly independent, we can transform them into a system of orthonormal vectors. It is possible. So we can transform the vectors into an orthonormal set of vectors by a very special process known as the Gram-Schmidt orthonormalization process. Of course, this has not been mentioned in the answer, but what we can see from the options is this one. It can be transformed into a set of orthonormal vectors. So option C shows that, therefore this problem has got two options B and C. So please go through these principles and it will help you to solve many more numerical problems.